Okay, good morning everyone. Good morning. So I want to spend time on one more short problem on plane wall conduction, okay? And then we'll move on to heat transfer through cylindrical bodies, which will be the motivation for studying cylindrical bodies is flow of fluid through pipes. Those are all cylindrical systems, so we would like to understand how heat is conducted through cylindrical pipes. Maybe we can come up with a way of insulating these, which could be a really great practical application. What is the thickness of the insulation that we need to provide? These are all questions one can ask, and I think we will be answering those questions during lecture, maybe not today but on Monday, okay? Alright, so one more problem on plane wall conduction. I'm given the following situation. Okay, so steady state. You're asked to assume that heat generation is positive, so Q dot is greater than 0. Okay, and then I'm given the following wall figure. Alright, so the left side of the wall is x is equal to minus L, that's the location. The right side of the wall is x is equal to plus L. The center line of the wall is x is equal to 0. Okay. And you are given the Dirichlet boundary conditions on the left and the right side. So which means you're given the temperature at the left and the right side. So given T at x is equal to minus L is some value T1, okay? T at x is equal to plus L is some value T2. You're asked to consider two cases when T1 is equal to T2. Second situation when T1 is greater than T2. There's also the third situation when T1 is less than T2. I'm not going to do that in class today, but I'll be having my lecture notes posted where I do that, I take care of that situation. So for both these situations, draw the temperature profile. So draw T of x for cases A and B. Okay? And this same problem can be solved for a situation where the heat generation is negative, Q dot is less than 0. Whatever we are going to do will be flipped. That's about it. But we'll see. Alright. I start off with the regular heat diffusion equation. Okay, one dimensional. We are assuming one dimensional heat flow. We are assuming things to be at steady state. We are assuming volumetric heat generation to be positive. Okay? These are the boundary conditions that are given to us. If you are given the surface temperature, they are the Dirichlet boundary conditions. So heat diffusion equation 1D. I typically write out the full thing. Okay, d square t dx square plus q dot is equal to rho c dt by dt. This is all regular stuff. We are at steady state, so the dt by dt term goes off. Okay, steady state. And now my partial differential equation becomes an ordinary differential equation. We have gone through this a couple of times in lecture, so I'm not going to go through the details. So d square t by dx square becomes minus q dot by k. Okay, and if I do the integration twice, which I'm not going to go through here because we've already done it, integrate twice. T of x is minus q dot x square by 2k plus c1x plus c2. So parabolic. No surprise. But things will start getting interesting pretty soon. Okay. What I'm going to do is I'm going to use the boundary conditions given to me, obtain C1 and C2 in terms of the values T1 and T2, and we will consider each of the cases, and we will see what the temperature profile looks like. Right? So substitute boundary conditions. So T at x is equal to minus L. If I do the substitution, that's minus q dot minus L whole square is still L square, so this is just L square by 2k minus C1L because x is equal to minus L plus C2. This is given to me as temperature T1. This is the first boundary condition. Second boundary condition, just plugging in, plus L minus q dot L square by 2k, that remains the same, plus C1L plus C2 is equal to T2. Call this as equations 1 and 2. Two equations, two unknowns. I can solve for C1 and C2. I don't remember the answer, so let me solve it. I subtract 1 from 2, I can get C1. Once I get C1, I can plug it back into either 1 or 2. No harm done. Okay? So 1 minus 2 minus C1L are the only terms remaining on the left hand side. So minus 2 C1L is T1 minus T2, or C1 is the following. Is minus T1 minus T2 by 2. I can take this and substitute it into either 1 or 2. It is going to give me the same thing, does not matter. Let me just do the substitution into 1. I'm going to have the following. So C2 is T1 minus q dot L square by 2k, bring it onto the right hand side, becomes a plus q dot L square by 2k minus C1 times L, bring it onto the other side, becomes a plus C1 times L, where C1 is still negative. So this is going to be minus T1 minus T2 by 2L times. Just algebra, okay, nothing fancy going on here. Cancel off the L's. T1, and then I have minus T1 by 2. I just add up things and I get the following. T1 minus T1 by 2 is T1 by 2. Minus and minus becomes a plus, so that's a plus T2 by 2. So this is T1 plus T2 by 2 plus q dot L square by So this is C2. Once again, we have done this with actual numerical values. Now we don't use values. These are the best type of problems where there are no numbers present. Okay, this is where thinking is involved. I take C1, I take C2, plug it back into T of x, I get my temperature profile. I take the first derivative, I get the slope. The slope of the temperature profile tells me the magnitude of the conduction flux. Okay, for a plane wall in this situation. So T of x, if I substitute it back, C2 will remain as it is. I'm going to take this q dot L square by 2k and club it together with this minus q dot x square by 2k, and I end up getting minus q dot by 2k x square minus L square. And then I have the C1 guy, which is minus T1 minus T2 by 2L times x. Alright. So I'm going to start collecting my results on one particular panel, and then we will keep referring back to it. Okay? So I'm going to write T of x. I'm going to take its derivative, and then we're going to start looking at the actual problem. When T1 is equal to T2, what happens? When T1 is greater than T2, what happens? Once we're done with this, we will go to radial heat transfer, or heat transfer in cylindrical bodies. Right? So T of x, T1, T2, divided by 2, and then the rest of that stuff, Q dot 2k, square minus L square, by 2. Okay, this is T2. Differentiate once. First term vanishes. From the second term, I'm going to get minus 2x by 2k. So that's going to be q dot x by 2 by k with a negative sign. Okay. Then the last term is going to give me minus t1 minus t2 by 2. Okay. These are the results that we will be using. One more thing I want to garner from these two equations is I want to find out between x is equal to minus L and between x is equal to plus L, is there a location x suffix I where the conductive heat flux is 0? Okay, so at x is equal to xi, I don't know this location at. I'm going to say that this is a location where the conductive flux is 0. I stand for insulation, right? If the conductive flux is 0 and I need to find that location, how do I find it? Yes?
Set that equation equal to 0?
Which equation?
The derivative?
The derivative, right. So this implies that dt by dx is 0 at x is equal to xi. Which tells me if I rearrange this, at x is equal to xi, I get the following. So xi is equal to minus t1 minus t2, and then I'm going to have k by 2L q dot. So three things that we have so far. One is this general temperature profile, which looks kind of scary. Its derivative, which is slightly less scary. And this is the saving grace. It will tell us where things are going to be 0. Okay? Now, let us look at the situation, and in the meantime, are there any questions? What are we trying to do? We are trying to draw the temperature profile. For two situations, when T1 is equal to T2, what is the temperature profile? Is it parabolic, but just with increasing slope or decreasing slope all the time, or does the slope become actually 0 at some point? And when T1 is greater than 0, what happens there? That's a much more trickier situation. Let me start off with T1 is equal to T2. Okay, so case A. Let's say that this is some temperature T. Okay. I first find out the value of xi. For case A, this is minus T1 minus T2 times something equal to 0. Makes sense to everybody, right? T1 is equal to T2. So at x is equal to xi, which is the center line in this case, the temperature, the derivative of the temperature profile is 0, which means that x is equal to 0 is the layer of the plane wall that is insulated, if I look at it from the three-dimensional viewpoint. My question to you, without doing the calculations, I'm going to do it. What is the direction of heat transfer? Is it from the left to the right or right to the left? Or is it something else?
Center outwards.
It has to always start from the center, go outward. That's what you're saying. Could it be a different situation? Could I have heat coming in from both sides and then joining at the center and becoming equal to 0? Could I have that?
Yeah, for a negative generation.
Yes, nice. So you already solved the problem in your mind. Let's do the math together and let's figure out, okay, without believing in ourselves, what does the math tell us? Okay? I start off by looking at the derivative. The key thing is the derivative. If the derivative at x is equal to minus L is positive, if the derivative at x is equal to plus L is negative, then I have the situation that you just described, where I have the center, x is equal to 0 is insulated, and heat is transferring out from the center onto the left and the right sides. Let's see if that is the case. So calculate the derivative. X is equal to minus L. Do the substitution. So T1 minus T2 by 2L is 0. So this just becomes minus Q dot by K times minus L. That's 0 because T1 is equal to T2. So this becomes a positive number. Exactly what our intuition is leading us to believe. Remember, if heat enters, it has to get out of this stuff somewhere. Okay? It cannot linger around. It's not a vandal. And x is equal to plus L, exactly similar scenario, but the antithesis of this, that's just minus Q dot by K times plus L. That guy is 0. This is now going to be negative because we have assumed positive heat generation. If I had assumed the heat generation to be negative, the tables would have been turned, and I would have had the situation where this slope would now become negative, this slope would become positive, and I would have the temperature at x is equal to 0 being the lowest of the two. Okay? So in this case, this is less than 0. Let's draw the profile. And if you want, you can figure out by saying, okay, hey, what is the temperature at x is equal to 0? When x is equal to 0, I have T1 plus T2 divided by 2 minus Q dot by 2K times 0 minus L square or plus Q dot L square by 2K, which is obviously greater than the temperature T of the walls. T1 plus T2 is equal to T. That is equal to T. So T plus a positive quantity is obviously greater than T if my heat generation is positive. If my heat generation is negative, T minus a quantity is going to be lesser than the side temperatures, which means that I'm going to have the x is equal to 0 location as the lowest temperature in the law. Okay? And now we plot the temperature profile. I know it's parabolic. I know the direction of the slope at x is equal to minus L and x is equal to plus L. I know the slope at x is equal to 0 is 0. Top and the bottom are insulated, so I don't care. Positive slope. Negative slope. And at x is equal to 0, the slope is 0. This is at x is equal to 0. And this goes back to the question that one of you had asked me last time, things that are 0, right? It makes sense. Let's do the more scarier scenario. T1 greater than T2. Many things can happen. Okay? And in some sense, this is how most engineering problems are, because you have all kinds of alternatives taking place, and as an engineer, you have to come up with your best guess. Okay? So for T1 greater than T2, let us start off by looking at what is the location x is equal to xi where the slope is 0. So this first of all tells me T1 minus T2 is positive. I don't know the extent of the value of T1 and T2, so you've got to bear with me on that. So xi, if I do the substitution, is minus T1 minus T2 k by 2L q dot. T1 minus T2 is greater than 0, positive heat generation. Thermal conductivity is never negative for the materials that we study. Length is a physical quantity. So everything in there is positive, but I have this negative sign, so this is going to be less than 0. So where do you think is the location along the wall where the conductive heat flux is 0? Is it to the left of 0 or the right of 0? It is to the right or left. So I should stand like this. Is it this way or that way? Well, now I can't see you. So it is obviously going to be to the left, but here is the problem. If T1 is much larger than T2, I can end up with a situation where this number, the magnitude of this number, is going to be greater than the magnitude of the length L. So there is a possibility that my location where the temperature flux, the conductive flux is 0, is not physically present in the wall at all because of the range of T1 and T2 values, which is the type of profiles that you have seen in the previous lecture. Okay? So you would have probably seen a profile where I start off at a negative slope, I go further down and the slope becomes more and more negative, which means that at no point in the temperature profile is the flux 0. And so I end up with the situation that I just described. But let us be a little more practical. Let us say that this is going to give me, this entire number here is going to give me something less than the magnitude of L. Okay, so let's say that is the less than the magnitude of L. So which means that xi can be anywhere between the following. Is obviously less than 0, is obviously less than minus L because I'm physically restricting the range of values for my temperatures T1 and T2. Does this make sense to everybody? Any questions? I want to do something more physical here, right? So that's the reason for taking it this way. Then let's do some derivatives. I want to slide this up. Alright, so let's calculate dt by dx at x is equal to minus L. At x is equal to minus L, just to take that creature, substitute it in there, so this is going to be plus q dot L by k, the first term, because I have a minus, the minus and minus L and minus term becomes a positive, and then minus T1 minus T2 by 2L. What do you think? Is the slope positive or negative? Good question.
You need the temperature.
I need physical values. Yes.
I would say positive because L is multiplied by Q dot and T1 minus T2 is not going to be bigger than L because we did that over there, right?
Well, I could choose the value of Q dot to be like really tiny.
That's true.
And I could choose the value of thermal conductivity to be really small, really large. I just take a huge concrete block and then look at heat transfer through that, right? Or no, not concrete block, I'm sorry, take a copper block or something like that and find the heat flux through that. So I have two situations now, but only one situation can fly.
Yeah, doesn't have to be positive because we were defined xi has to be in this range somewhere. But like it's that derivative test, we know that both slopes are pointing towards it.
Okay, so you hit the nail on the head. Let me walk through the math, okay, and then I'll explain the point that he just made. For the time being, I'm going to assume that this quantity is very small so that this is less than 0. Okay, so let's say, just for kicks, Q dot L by K is less than the magnitude of this, which tells me that this slope is negative. Okay, if this is the situation that I have assumed. dt by dx at x is equal to plus L. What is that going to be? Minus Q dot L by K, just substitute. Minus T1 minus T2 by 2L. T1 minus T2 is positive, Q dot is positive, L is positive, K is positive. So this is just going to give me a giant negative number. No matter what you do, this quantity is always going to be negative. For the condition that we have, assume T1 greater than T2. So now I am in this very interesting situation in life. Where I have the following. I have a negative slope at the left side of the wall. I have a negative slope at the right side of the wall. I have a 0 slope at x is equal to xi. If I calculate the temperature at x is equal to xi, if this temperature is going to be less than T2 and less than T1, then I am actually okay. Then I can have heat transfer taking place in the directions that we have just looked at. Okay, I can have heat coming in through the left side, heat coming in through the right side. If temperature gradient is less than 0, it means it is the heat coming in through that side. If temperature gradient is positive, it means heat is escaping through that side. Conductive flux is escaping through that side. Okay? If I calculate this value, and I'm not going to do the calculations, you can figure it out. I'll have it posted on my notes. This will end up being greater than T1. Okay, please see my lecture notes that I'll post. Does that make any physical sense? If I draw it out, this is the situation that is being described. I have a negative slope here, a negative slope there. That's obviously the slope on the x is equal to plus L side is much larger in magnitude than on the x is equal to minus L side. It is obvious to see from the magnitudes there. And at some point I have 0 x is equal to 0. So at x is equal to xi, my slope is 0. So that my profile will look something of that sort, where this is the slope. This cannot happen because if you go through the math, you will find out that the temperature at x is equal to xi, given the range of values that we have assumed for T1 and T2, and this inequality here, it cannot be true. I cannot have a temperature that is higher here, a temperature that's lower than these two, and the heat cannot come in. Okay, so this is unphysical. Does this make sense to everybody? Any questions or thoughts on what we've done so far?
So that case would be possible if Q dot was taking heat out more so, right?
Right. Absolutely. Right. Right. So you can't have heat entering in, and you can't have heat entering in, and then the temperature here is going to be lower than the temperature here and there. But we just proved that the temperature there is higher. Okay. So this is an impossible situation. So the reality is that this has to be flipped. This inequality. That cannot be true for the situation that we have assumed. Okay. So then I flip it out and I get the following. So dt by dx at x is equal to minus L, it has to be greater than 0. At x is equal to plus L is obviously less than 0 no matter what you do, and magnitude of q dot L by K, this has to be greater than magnitude of this particular quantity. Okay, this is the only physical situation that you can have, and if you draw it out, here is what it will look like. X is equal to 0, center line. Okay, x is equal to I or xi, where I have the slope being 0. X is equal to plus L and x is equal to minus L. Slope at x is equal to plus L is negative. What can you say about the slope at x is equal to 0? Is it positive or negative? Slope at x is equal to plus L is negative, so slope at x is equal to 0 has to be negative. Okay, because my insulation condition starts before x is equal to 0. Okay, so I have the following situation then. This is the profile of the temperature. This is a 0 slope at x is equal to xi. This is a positive slope as I start off, and as you can see, at x is equal to 0, the slope is lesser in magnitude than x is equal to plus L, but it is still negative, it is descending. And this magnitude is much more so than what I started off at x is equal to plus minus L. Okay? And so this obeys all the constraints of the problem. T at x is equal to xi is going to be larger than T1 and T2. No changes on that. This criterion has to be met for this problem to physically have a profile of the following sort. If this x is equal to xi does not lie physically within the limits from 0 to minus L, then anything else can happen. Then I can have a situation that I have just described. Okay? I'm not going to go through the details of that. Maybe you'll have that as your homework problem next week. Question?
So, in over there you assume that q dot was negative.
No, q dot is always positive for us. When we started the problem, q dot is always positive. Heat generation is positive.
Oh, okay.
Right. This is a problem where heat generation is always positive.
Okay.
Okay? All I'm saying is that if I'm looking at this situation here, I have two choices. depending on the magnitude of this quantity versus the magnitude of that quantity, this slope can either be less than 0 or greater than 0. If this guy is less than 0, I end up with a very sad situation here, where I have heat entering in, and essentially the temperature there, I have found out, and you'll see the math, the temperature is greater than T1, so that cannot be the case. Okay? Yes, sir.
Could you maybe explain how we could intuitively look at that and know why it's that and not that? Or do we have to go through the math?
You could intuitively look at it. I mean, if you have heat coming in through both sides, right, then what's going to happen is that the temperatures at the edges must be greater than the temperature at the x is equal to xi location. But of course, you have to go through the math to figure out what T1 is, T at xi is, and then you'll see that, okay, that cannot happen.
Thank you.
And that's for positive heat generation.
I just want to get clarification for that graph over there. Is it the slope is negative at both sides or negative at one side?
Negative at both sides, in a sense that,
That looks fine.
oh, I'm sorry, I should have drawn it as negative here. Yeah, that's my mistake. Right. Something, thank you. Right. So heat is entering through here, and now it might make more sense to see what's going on.
Thank you.
Thank you for coming. Okay. So this is the situation for T1 greater than T2, and for the constraints of the problem where I am physically located within the limits of x is equal to 0 and x is equal to minus L for the insulated surface. Okay. And I have the third situation also drawn up. I'll post that on the lecture notes, and you can flip the tables. Say Q dot is negative. What happens to the entire situation? All the plots will be flipped out. Yes.
Why, when the conductive flux is 0, why is the derivative of the temperature profile? How are those correlated?
Oh, by Fourier's law, Q double prime is minus K dt by dx. Okay. Any last thoughts on this problem? Before we go on to heat transfer in cylindrical bodies. Alright, so I'll move on. So now we're always going to be doing 1D conduction only in this particular course. 2D conduction falls outside the realm of what you're doing because you have to end up solving the Laplace equation. Not the Laplace transform, the Laplace equation, the partial differential equation. And we will not be doing that. Okay? Laplace transforms are okay. You'll see them when we do transient conduction very soon. Alright, so radial systems. Heat transfer in radial systems. So this could either be cylindrical geometry or spherical geometry. Cylindrical geometry is, as an engineer, more fascinating because of all these pipes that are carrying heat or cold fluid from one region to the other. You can have pipes inside reactors and so on, which are also going to be doing something similar. Yes, ma'am. Question.
Just really quick, is there a difference between Q dot and Q double prime? I thought they both had flux.
No, Q dot is volumetric heat generation. Right, that's always the thing that we've been using. So, in the first lecture I told you that in thermodynamics you would have come across Q dot. That is no longer going to be the case for us. I'm going to call that fellow just Q. Okay, so maybe just to refresh your memories, Q is rate of heat transfer in watts. This is what you would have seen in thermodynamics as Q dot. Why I am not using Q dot is because your textbook does not use Q dot. It's as simple as that. Q double prime is conductive flux or flux in general, not conductive necessarily, which is watts per meter square. And then Q dot is volumetric heat generation or energy generation. And this is in watts per meter cube. Okay. Alright, so radial systems, very nice practical applications. We will reach the problem of what is the critical thickness of an insulation that you need to have around a pipe. Something very practical. If you open up the roof of your home, you'll see these things there. Please don't do that. Alright, there's a big difference between plane conduction and conduction through cylindrical bodies. Here is the difference. Okay. Okay, so this is a plane wall. I'm going to draw a cylindrical pipe as well, a pipe system. Okay. We are going to assume a couple of things. As we did for plane walls, we are going to assume that the direction of heat transfer is only in one dimension. Okay. If I have a cylindrical body, I have three potential directions of heat transfer: radial, circumferential, and then along the length of the tube, which is the generator direction or the axial direction. We are going to consider only radial heat transfer. Okay, which means that when I look at the conductive flux will have a direction that is normal to the surface of the cylindrical body. So if I look at some point on this body here, and if I draw the normal vector, it's going to be pointing out. Okay, this is normal to the surface, this is a curved surface. Okay, if I look at a curved surface, I can draw three vectors or three unit vectors, right? I can draw a tangential unit vector, E suffix t. I can draw an axial unit vector, E suffix z. Okay, and then I can draw a radial or a normal unit vector, which I call as E suffix r. Et is typically called as E theta, if you like. We will not be looking at heat transfer in these directions. We will be looking only in the radial direction. So if I draw a two-dimensional view of this situation, direction of heat transfer is always radial. Okay, so this is always going to be my ER, ER, ER. Radial heat transfer only for this particular course. What is the reason for bringing a plane wall? If I look at the plane wall, if I look at any location, let's say that this is the direction of heat transfer, if I look at any location, the surface area is always a constant. Right? If I shade this area here, the surface area for heat transfer is always a constant. It does not change with the axial location x. So for plane wall, I'll write this out here. The surface area for heat transfer is constant. As you can see, that's a shaded area. As I travel along the x is equal to 0 or minus L or plus L location, surface area never changes. That's not the case for cylindrical bodies. I'm going to draw two situations. Okay, so watch this. Okay. Now, if I say that this is a cylindrical pipe, okay, there's fluid flowing through the annular region of the pipe, but let's say that it has an inner and outer radius of R0 and Ri. R0 and Ri. Radii. O is for outer, I is for inner. If I look at the surface area for heat transfer and looking at the inner radius, this is all I'm going to be looking at. This is the surface area for heat transfer, because I'm assuming that heat transfer is only radial, so the direction of heat transfer is going to be aligned with the direction of the area normal in the radial direction. And this is nothing but if I call this length as L, what is the surface area? 2 times pi times Ri times that. If I look at heat transfer on the outer radius, it's all of these areas. The outer radius is R naught, which means that the amount of area required for heat transfer or available for heat transfer is A naught, which is 2 pi R naught times L. So clearly this is not the same as the inner surface area available, and so this is a big difference between plane conduction and radial heat transfer. Same goes for spherical bodies as well. For spherical bodies, surface area is 4 pi R square. So if I'm looking at inner radius, it's 4 pi Ri square. Outer radius 4 pi R naught square. No big difference. Okay? So for radial heat transfer, surface area is a function of radius. Okay. So now I'm going to do a very quick derivation of the heat diffusion equation for cylindrical bodies. I will set up the derivation, and then if there is time we'll complete it. If not, I'll have it posted on my notes. I want to get the equation, that's all I need. Okay? So heat diffusion equation for cylindrical bodies. We're going to assume the density of the body is rho. Thermal conductivity is K. I'm going to assume this is constant. Okay? Why not? Right? Then C is the specific heat. Could be specific heat at constant pressure or volume, but if you're doing a compressible body, incompressible body, it's pretty much the same. Cp is equal to Cv. And I'm going to consider a cylindrical body here, as I'm going to draw it, solid cylinder. Direction of heat transfer is only radial. Okay, so I'm going to consider a small volume element which is going to be drawn along the length of the cylinder. So this length is L. Okay, so this is my small volume element, which means that it is in the form of an annular ring, okay, or it's in the form of a cylindrical shell element. I'm going to take the creature out and I'm going to draw the direction of conductive heat flux. Radii, some radius r, the thickness of this element is dr or delta r. Okay, so for the time being it is delta r.